Hello everyone, welcome back. So today in this video we'll be talking about the adjusted R square. So we have discussed what R square is. So for the simple regression model, we use the notation small r, right? When we talk about R square, and for the multiple regression model, we use the term capital R square, right? So we'll talk about adjusted R square today. Okay. So an important property. So R square is a non-decreasing. Okay, non-decreasing. So it might not be increasing. Okay, but it is non-decreasing. Okay, so the value that is there, it will not fall from that value. It can increase. It can stay the same, but it will not fall. So R square is a non-decreasing function of the number of explanatory variables or regressors present in the model. Okay, so R square is basically talking about what percentage of the variability in the regressant is being explained by the regressors. So if I add extra regressors in the model, it means that more of the variation in the y variable or the regression can be explained now. So that is why. So either more or at least the same level as the previous one. So that is why a non-decreasing function. So it will. So as you add the variables, it will not be the case that the amount explained by the variables will fall or the R square value will fall. It will either stay the same or it will increase. So present in the model unless the added variable is perfectly collinear with the other variables as the number of regressors increase. So unless this is the case where there is a perfect collinearity between the regressors, unless this is the case, uh, till then your R square is a non-decreasing function of the number of explanatory variables or regressors present in the model. Okay. So as the number of regressors increase, R square almost invariably increase and never decrease. Okay. So R square is equal to ESS upon TSS, and R square is equal to 1 minus RSS upon TSS. This is the formula, we already know these formulas, right? So R square is basically 1 minus summation UI hat square upon summation YI square, right? So summation, we know that summation y small yi square is independent of the number of x variables in the model because it is simply the deviation from the mean value, right? But the RSS, which is summation ui hat or the summation of the error terms, square of the error terms, depends on the number of regressors because it is capturing the unexplained part in the y variable. So if the number of x variables are increasing, it means the non-explained part, that is the ui, is decreasing, right? So it depends on the number of regressors present in the model. So as the number of x variables increase, summation ui hat square is likely to decrease, hence r square will increase. Okay, so if you see this formula, so if you're adding the variables, x variables, extra x variables, it means that this value is increasing. Oh, sorry, this value is decreasing because the non-explained part is being reduced now. So this value is decreasing, this value is almost the same. This entire value is decreasing, and the value of this, because it is 1 minus a value that is falling, it means that the value of r square is increasing, right? That is more and more variability in the y variable is now being explained by the x variables. Therefore, when comparing two regression model with the same dependent variables but differing number of x variables, one should be wary of choosing the model with the highest r square, because higher the r square, it means that uh, more the explanation of the y variable is being explained, right? So let me just repeat the sentence. So So therefore, when comparing two regression models with the same dependent variable but differing number of x variables, one should be wary of choosing the model with the highest R square, right? Because higher R square implies better explanation of the variation in the Y model, or more explanation of the variation in the Y model, and it also means that more of regressors are being added. It also means that the error term or the unexplained part is decreasing, right? Now, to compare two R square terms, one must take into account the number of X variables present in the model. Therefore, we use adjusted R square. Okay, so adjusted R square is doing what? It is basically helping you or allowing you to compare two models where the number of variables in the models might be different. Okay, how? So you adjust the formula of R square. So you add the degrees of freedom here and here also, in the numerator and the denominator. So your degrees of freedom will depend on the number of variables or the number of parameters in the model, including the intercept term. This k here is basically the number of parameters in the model, including the intercept term. So your degree of freedom will now affect the R square value, and this new R square value is called your adjusted R square, because you are taking in the factors of the extra variables that are being added. So more the variables, more or at least the same explanation of the regressant, right? So that is being uh, allowed by the adjusted R square. So adjusted means adjusted for degree of freedom associated with the sum of squares entering in R square. So summation ui hat square has n minus k degrees of freedom, and summation small yi square has n minus 1 degrees of freedom, because there is only one thing that is restricting it, that is the y bar that we have to compute, right? That is why only n minus 1 degrees of freedom. So R square or adjusted R bar square, sorry, and also called as adjusted R square, is basically computed by this formula also. It is 1 minus sigma hat square upon uh, small s square upon y. So sigma hat square is the variance of the residual term, right? And your small s square y is basically the sample variance of your y variable, right? All these terms are affected by their degrees of freedom, and that is why we can also compute the adjusted R square using this formula. It's the same thing as we had seen in the previous slide. So now, what is the relation between your adjusted R square and your R square? So it is given by this formula, where adjusted R square is basically equal to 1 minus R square upon the degree of freedom of the residual of the y yi minus y bar, this term, and upon the degrees of freedom of the residual term, right? So this term here is being multiplied by 1 minus R square, and this entire term is being subtracted by 1 minus by 1. So that is how you get this relationship between your adjusted R square and your R square. This is your R square, this is your adjusted R square, and they are linked using this ratio n minus 1 upon n minus 2, which is the ratio of the degrees of freedom of the two variable of the two sum of squares that entered this formula, or the formula of your R square that was here, right? So if k is more than 1, okay, so at k equal to 1, your R bar square will be equal to R square. If you see this formula, if k is equal to 1, then this entire term becomes 1, and if you solve this, you will get R bar square equal to R square. And but if k is more than 1, this implies that as the number of x variables increase, adjusted R square increases less than the unadjusted R square, and adjusted R square can be negative, while r square cannot be negative. It can be 0, but it cannot be negative, right? So if the number of variables are increasing in the model, it means that your adjusted r square is increasing less than compared to your unadjusted r square. So in that sense, your adjusted r square is somewhat giving a better or more exact picture of the fit of the model, or of the regression line, right? So r square value might overestimate the degree of fit of the regression line, but since your r bar square, that is the adjusted r square, is also taken into the factor the degrees of freedom, it means that it is giving a better picture of the fit of the model, of the regression line in the model, right? So in that sense, r bar square is better, somewhat better compared to your r square. In case r square turns out to be negative, so your r bar square can be negative, that is also a property of your r bar square, while we know that the r square cannot be negative. In case r square turns out to be negative, so if in any model using a data, if you try to regress a equation and you find out that r square is negative, then its value is taken as 0. So it can never be taken as negative. If it ever comes out to be negative, then its value is taken to be 0. It means that uh, the model doesn't fit, or the model that you have created doesn't fit around the data that you had. Okay. So which is better, r square or r bar square? We just discussed. And okay, so if uh, if you somewhere cannot calculate your r bar square, okay, so then there's also a term called modified r square, which is also somewhat better compared to your r square, because it can equally be used to uh, check for the goodness of fit. So it is a modified form of your r square, which is used to have a better picture of the degree of fit, goodness of fit, right? And it is calculated using this formula, which is r square is equal to 1 minus k by n. K is the number of variables, and is the sample size into r square, right? So this was all for the video, and so let's just let's also talk about this. So now we have learned about adjusted r squares, which is given by r bar square, and we also have the idea about r square. So now suppose you want to compare two r square values. Okay, now we are not talking about r bar square, we have compared two r square values. Now for comparison, the sample size n and the dependent variable must be the same. So this is a precondition if you want to compare two r square. This is about r square, not r bar square. Okay, so the explanatory variable may take any form. So your n, or the sample size, and the number of dependent variable, that is your y variable, that should be the same, and your x variable can take any form, or be it simple form, simple regression form, or the multiple regression form. So if that is the case, then you can compare two r squared. So this is the example where you can't compare two r squared. Okay, ln yi plus is equal to beta 1 plus beta 2 x2y plus beta 3 x3y plus gy, and yi is equal to alpha 1 plus alpha 2 x2y plus alpha 3 x3y plus gy. So why can't we compare these two equations using r square? Because in the first equation, r square is measuring your variation in ln y, right? And in the second equation, it measures the variation in y explained by x2 and x3. So in both the cases, different variables are being measured. Okay, in here it's ln y that is being measured, in here y is being measured. So that is why your r square can't be compared for these two equations, and that is why this condition is required, that the sample size should be the same and the dependent variable must be the same. So had this been just yi, then we could have compared the model using r square, right? So yeah, so I think this is all for this video. We'll talk about polynomial regression function in the next video. I hope the concept of r square and adjusted r square is clear now. So I'll see you in the next video. Till then, take care.